Semiconductors are the unsung heroes of the digital age. They are the tiny chips that power our smartphones, computers, cars, and countless other electronic devices. Without semiconductors, our world would be a very different place. But what exactly are semiconductors? And how do they work? In simple terms, semiconductors are materials that have a conductivity between that of a conductor, like copper, and an insulator, like rubber. This unique property allows them to control the flow of electricity in a very precise way. The key to understanding semiconductors lies in their atomic structure. Semiconductors, such as silicon, have 4 electrons in their outermost shell. These electrons are called valence electrons, and they are responsible for forming chemical bonds with other atoms. In a pure semiconductor crystal, each atom shares its valence electrons with its neighbors, forming a stable and electrically neutral structure. However, this perfect balance can be disrupted by introducing impurities, a process called doping. Doping involves adding a small amount of atoms from a different element to the semiconductor crystal. These impurities can either donate extra electrons, N-type doping, or create holes where electrons are missing, P-type doping. The introduction of electrons or holes dramatically alters the electrical properties of the semiconductor. N-type semiconductors have an excess of negative charge carriers, electrons, while P-type semiconductors have an excess of positive charge carriers, holes. Doping allows us to precisely control the conductivity of semiconductors. By carefully adjusting the type and concentration of dopants, we can create semiconductors with a wide range of electrical properties. For example, a heavily doped semiconductor will have a high conductivity, while a lightly doped semiconductor will have a low conductivity. This ability to fine-tune conductivity is essential for creating electronic devices with specific functions. Furthermore, the interaction between electrons and holes in doped semiconductors gives rise to unique electrical phenomena that are exploited in various electronic devices, such as diodes and transistors. When a P-type semiconductor and an N-type semiconductor are brought into contact, they form a p-n junction. This junction is the fundamental building block of many electronic devices, including diodes and transistors. At the p-n junction, electrons from the N-type region diffuse into the P-type region, while holes from the P-type region diffuse into the N-type region. This diffusion creates a region called the depletion region, where there are no free charge carriers. The depletion region acts as a barrier to the flow of current. However, by applying an external voltage, we can control the width of the depletion region, and thus the flow of current through the p-n junction. Transistors. The tiny switches that power our world. Transistors are miniature electronic switches that can amplify or switch electronic signals and electrical power. They are the fundamental building blocks of modern electronics, enabling the creation of integrated circuits that contain billions of transistors on a single chip. A transistor consists of 3 semiconductor regions: an emitter, a base, and a collector. The base region controls the flow of current between the emitter and the collector. By applying a small voltage to the base, we can control a much larger current flowing between the emitter and the collector. This ability to amplify signals is what makes transistors so versatile and powerful. Diodes. Guiding the flow of electricity. Diodes are 2-terminal electronic components that allow current to flow in only one direction. They are essentially one-way valves for electricity, blocking current flow in the reverse direction. Diodes are based on the p-n junction. When a positive voltage is applied to the P-type side of the diode, current flows easily through the device. However, when a negative voltage is applied, the depletion region widens, blocking the flow of current. This unidirectional current flow property makes diodes useful in a wide range of applications, such as rectifying alternating current, AC, to direct current, DC, protecting circuits from voltage spikes, and generating light in light-emitting diodes, LEDs. Semiconductors as eyes. Some semiconductors exhibit a remarkable property. They are sensitive to light. When light strikes the surface of these materials, it can excite electrons, generating a current. This phenomenon is known as the photoelectric effect. Photodiodes and phototransistors are semiconductor devices that exploit the photoelectric effect. They are used in various applications, including light detection, solar cells, and optical communication systems. The sensitivity of semiconductors to light has revolutionized fields like photography, energy, and telecommunications, enabling the development of digital cameras, solar panels, and fiber optic cables. Silicon is the most widely used semiconductor material due to its abundance, low cost, and favorable electrical properties. However, other materials such as germanium, gallium arsenide, and indium phosphide are also used in specific applications. Each semiconductor material has its own unique set of properties, such as band gap energy, electron mobility, and thermal conductivity. These properties determine the material's suitability for particular applications. For example, gallium arsenide has a higher electron mobility than silicon, making it suitable for high-speed electronics. Indium phosphide is used in optoelectronic devices due to its efficient light emission properties. From smartphones to satellites, semiconductors are the heart of countless electronic devices that we rely on every day. From smartphones and laptops to cars and airplanes, semiconductors play a crucial role in modern technology. In smartphones, semiconductors power the display, processor, memory, and communication systems. In cars, they control the engine, brakes, and safety features. In medical devices, they enable advanced imaging and diagnostics. The ubiquitous presence of semiconductors in our lives is a testament to their versatility and importance. They have revolutionized the way we live, work, and interact with the world around us. Shaping the future, one chip at a time. Semiconductors are the foundation of modern electronics, enabling the creation of devices that have transformed our world. Their unique properties such as variable conductivity, light sensitivity, and ability to amplify signals have led to countless innovations. As technology continues to advance, the demand for smaller, faster, and more efficient semiconductors will only grow. Researchers are constantly exploring new materials, fabrication techniques, and device architectures to push the boundaries of semiconductor technology. The future of electronics is inextricably linked to the advancement of semiconductors. From artificial intelligence and quantum computing to personalized medicine and space exploration, semiconductors will continue to shape the future, one chip at a time.
The first rule of channel is subscribe channel. Second rule of channel is click like. This channel will make you smart.